So what you see here, this is a screenshot of the Desmos online graphing calculator. You can use it at desmos.com, and I encourage you to use this after this video or even while I'm doing this video. But the goal here is to think about reflection of functions. So let's just start with some examples. Let's say that I had a function f of x, and it is equal to the square root of x. So that's what it looks like, fairly reasonable. Now let's make another function, g of x, and I'll start off by also making that the square root of x. So no surprise there, g of x was graphed right on top of f of x. But what would happen if, instead of it just being the square root of x, what would happen if we put a negative out front right over there? What do you think is going to happen when I do that? Well, let's just try it out. When I put the negative, it looks like it flipped it over the x-axis. It looks like it reflected it over the x-axis. Now, instead of doing it that way, what if we had another function, h of x, and I'll start off by making it identical to f of x. So once again, it's right over there. It traces out f of x. Instead of putting the negative out in front of the radical sign, what if we put it under the radical sign? What if we replaced x with a negative x? What do you think is going to happen there? Well, let's try it out. If we replace it, that shifted it over the y-axis. And then pause this video and think about how would you shift it over both axes? Well, we could do I'm running out of letters. Maybe I will do I don't know, k of x is equal to, so I'm going to put the negative outside the radical sign, and then I'm going to take the square root, and then I'm going to put a negative inside the radical sign, and notice, it flipped it over both. It flipped it over both the x-axis and the y-axis to go over here. Now, why does this happen? Well, let's just start with the g of x. So when you put the negative out in front, when you negate everything that's in the expression that defines the function, whatever value you would have gotten of the function before, you're now going to get the opposite of it. So when x is 0, we got 0. When x is 1, instead of 1 now, you're taking the negative of it, so you're going to get negative 1. When x is 4, instead of getting positive 2, you're now going to get negative 2. When x is equal to 9, instead of getting positive 3, you now get negative 3. So hopefully that makes sense why putting a negative out front of an entire expression is going to flip its graph over the x-axis. Now what about replacing an x with a negative x? Well, one way to think about it now is whenever you inputted 1 before, that would now be a negative 1 that you're trying to evaluate the principal root of. And we know that the principal root function is not defined for negative 1. But when x is equal to negative 1, our original function wasn't defined there when x is equal to negative 1. But if you take the negative of that, well, now you're taking the principal root of 1. And so that's why it is now defined. So whatever value the function would have taken on at a given value of x, it now takes that value on the corresponding opposite value of x, and on the negative value of that x. And so that's why it flips it over the y-axis. And this is true with many types of functions. We don't have to do this just with a square root function. Let's try another function. Let's say we tried this for e to the x power. So there you go. We have a very classic exponential there. Now let's say that g of x is equal to negative e to the x. And if what we expect to happen happens, this will flip it over the x-axis. So negative e to the x power. And indeed, that is what happens. And then how would we flip it over the y-axis? Well, let's do an h of x. That's going to be equal to e to the, instead of putting an x there, we will put a negative x. Negative x. And there you have it. Notice it flipped it over the y-axis. Now both examples that I just did, these are very simple expressions. Let's imagine something that's a little bit more complex. Let's say that f of x, let's give it a nice higher degree polynomial. So let's say it's x to the third minus 2x squared. That's a nice one. And actually, let's just add another term here. So plus 2x. Oh no, I want to make it minus 2x. I want to accentuate some of those curves. All right, so that's a pretty interesting graph. Now, how would I flip it over the x-axis? Well, the way that I would do that is I could define a g of x I could do it two ways. I could say g of x is equal to the negative of f of x, and we get that. So that's essentially just taking this entire expression and multiplying it by -1. And notice, it's multiplying it, it's flipping it over the x-axis. Another way we could have done it is, instead of that, we could have said the negative of x to the third minus 2x squared, and then minus 2x, and then we close those parentheses, and we get the same effect. Now, what if we wanted to flip it over the y-axis? Well, then instead of putting a negative on the entire expression, what we want to do is replace our x's with a negative x. So you could do it like this. You could say that that's going to be f of negative x. And that has the effect of everywhere you saw an x before, you replace it with a negative x. And notice, it did exactly what we expect. It flipped it over the y-axis. Now, the other way we could have done that, just to make it clear, that's the same thing as negative x to the third power minus 2 times negative x squared minus 2 times negative x. And of course, we could simplify that expression, but notice it has the exact same idea. And if we wanted to flip it over both the x and y axes, well, we've already flipped it over the y-axis. To flip it over the x-axis, oh, whoops, I just deleted it. To flip it over the, I'm having issues here. To flip it over the x-axis as well, we would, oh, it gave me a parentheses already. I would just put a negative out front. So I put a negative out front, and there you have it. This flipped it over both the x and y-axis. You can do them in either order, and you will get to this green curve. Now, an easier way of writing that would have been just the negative of f of negative x, and you would have gotten to that same place. So go to Desmos, play around with it. Really good to build this intuition and really understand why it's happening. What we're going to do in this video is do some practice examples of exercises on Khan Academy that deal with reflections of functions. So this first one says this is the graph of function f, fair enough. Function g is defined as g of x is equal to f of negative x, also fair enough. What is the graph of g? And on Khan Academy it's multiple choice, but I thought for the sake of this video it'd be fun to think about what g would look like without having any choices, just sketching it out. So pause this video and try to think about it, at least in your head. All right, now let's work through this together. So we've already gone over that g of x is equal to f of negative x. So whatever the value of f is at a certain value, we would expect g to take on that value at the negative of that. So for example, we can see that f of 4 is equal to 2. So we would expect g of negative 4 to be equal to 2. Because once again, g of negative 4, we could write it over here. G of negative 4 is going to be equal to f of the negative of negative 4, which is equal to f of 4. And so we could keep going with that. What would g of negative 2 be? Well, that would be the same thing as f of 2, which is 0. So it would be right over there. What would g of 0 be? Well, that would be the same thing as f of 0, because the negative 0 is 0. And f of 0 is right over there. It looks like negative 2. And so you can already see where this is going. And we've already talked about it in previous videos, that if you replace your x with a negative x, you're essentially reflecting over the y-axis. So g is going to look something like this. It is going to look something like this. Once again, g of negative 6 would be the same thing as f of 6. And so that would be the graph of g. And if you're doing this on Khan Academy, you'd pick the choice that looks like this. That would give a reflection over the y-axis. Let's do another example. So here, once again, this is the graph of the function f. And then they say, what is the graph of g? And so pause this video and at least try to sketch it out in your mind what g should look like. All right, so in this situation, they didn't replace the x with negative x in f of x. Instead, g of x is equal to the negative of all of f of x. In fact, we could rewrite g of x like this. We could say that g of x is equal to, notice, all of this right over here, that was our definition of f of x. So g of x is equal to the negative of f of x. So instead of it being f of negative x, it's equal to the negative of f of x. So one way to think about it is, we can see that f of 0 is 2, but g of 0 is going to be the negative of that. So it's going to be equal to negative 2. And so you could keep going with that. You could see that whatever f of a certain value is, g of that value would be the negative of that. So it would be down here. And so g of x would be a reflection of f of x about the x-axis. So g of x is going to look something like that, a reflection about the x-axis. And so once again, I'm kind of going to pick the choice that would actually look like that. Let's do another example. This is strangely fun. So this is a screenshot of Desmos. It's an online graphing calculator. And what we're going to do is use it to understand how we can go about scaling functions. And I encourage you to go to Desmos and try it on your own, either during this video or after. So let's start with a nice, interesting function. Let's say f of x is equal to the absolute value of x. So that's pretty straightforward. Now let's try to create a scaled version of f of x. So we could say g of x is equal to, well, I'll start with just absolute value of x. So it's the same as f of x. So it just traced g of x right on top of f. But now let's multiply it by some constant. Let's multiply it by 2. So notice the difference between g of x and f of x. And you can see that g of x is just 2 times f of x. In fact, we can write it this way. We can write g of x is equal to 2 times f of x. We get to the exact same place. But you can see that as our x increases, g of x increases twice as fast, at least for positive x's, on the right-hand side. And actually, as x decreases, g of x also increases twice as fast. So is that just a coincidence that we have a 2 here and it increased twice as fast? Well, let's put a 3 here. Well, now it looks like it's increasing 3 times as fast. And it does that in both directions. Now, what if we were to put a 0.5 here? 0.5. Well, now it looks like it's increasing half as fast. And that makes sense because we are just multiplying, we are scaling how much our f of x is. So before, when x equals 1, we got to 1. But now when x equals 1, we only get to 1/2. Before, when x equals 5, we got to 5. Now when we get to x equals 5, we only get to 2.5. So we're increasing half as fast, or we have half the slope. Now, an interesting question to think about is, what would happen if, instead of it just being an absolute value of x, let's say we were to have a non-zero y-intercept. So let's say, I don't know, plus 6. So notice, then when we change this constant out front, it not only changes the slope, but it changes the y-intercept because we're multiplying this entire expression by 0.5. So if you multiply it by 1, we're back to where we got before. And now if we multiply it by 2, this should increase the y-intercept because remember, we're multiplying both of these terms by 2. And we see that. It not only doubles the slope, but it also increases the y-intercept. If we go to 0.5, not only did it decrease the slope by a factor of 1/2, or I guess you could say multiply the slope by 1/2, but it also made our y-intercept be half of what it was before. And we can see this more generally if we just put a general constant here, and we can add a slider. And actually, let me make the constant go from 0 to 10 with a step of, I don't know, 0.05. That's just how much does it increase every time you change the slider. And notice, when we increase our constant, not only we're getting narrower because the slope, the magnitude of the slope is being scaled, but our y-intercept increases. And then as k decreases, our y-intercept is being scaled down, and our slope is being scaled down. Now that's one way that we could go about scaling, but what if instead of multiplying our entire function by some constant, we instead just replace the x with a constant times x? So instead of k times f of x, what if we did f of k times x? Another way to think about it is g of x is now equal to the absolute value of kx plus 6. What do you think is going to happen? Pause this video and think about it. Well, now when we increase k, notice it has no impact on our y-intercept because it's not scaling the y-intercept, but it does have an impact on slope. When k goes from 1 to 2, once again, we are now increasing twice as fast. And then when k goes from 1 to 1/2, we're now increasing half as fast. Now this is with an absolute value function. What if we did it with a different type of function? Let's say we did it with a quadratic. So 2 minus x squared. And let me scroll down a little bit. And so you can see when k equals 1, these are the same. And now if we increase our k, let's say we increase our k to 2, notice our parabola is, in this case, decreasing as we get further and further from 0 at a faster and faster rate. That's because what you would have seen at x equals 2, you're now seeing at x equals 1 because you are multiplying 2 times that. And so, and then if we go between 0 and 1, notice on either side of 0, our parabola is decreasing at a lower rate. It's a changing rate, but it's a lower changing rate. I guess you could put it that way. And we could also try just to see what happens with our parabola here. If instead of doing kx, we once again put the k out front, what is that going to do? And notice that is changing not only how fast the curve changes at different points, but it's now also changing the y-intercept because we are now scaling that y-intercept. So I'll leave you there. This is just the beginning of thinking about scaling. I really want you to build an intuitive sense of what is going on here and really think about mathematically why it makes sense, and go on to Desmos and play around it with yourself and also try other types of functions and see what happens. So we're told this is the graph of function f right over here. And then they tell us that function g is defined as g of x is equal to 1/3 f of x. What is the graph of g? And if we were doing this on Khan Academy, this is a screenshot from our mobile app. It has multiple choices, but I thought we would just try to sketch it. So pause this video, maybe in your mind, imagine what you think the graph of g is going to look like, or at least how you would tackle it. All right, so g of x is equal to 1/3 f of x. So for example, we can see here that f of 3 is equal to -3. So g of 3 should be 1/3 that. So it should be -1. Likewise, so g of 3 would be right over there. And likewise, g of -3, what would that be? Well, f of -3 is 3. So g of -3 is going to be 1/3 that, or it's going to be equal to 1. F of 0 is 0. 1/3 of that is still 0. So g of 0 is still going to be right over there. And we know that's going to happen there and there as well. And so we already have a sense of what this graph is going to look like. The function g is going to look something like this. I'm just connecting the dots. And they did give us some dots that we can use as reference points. So the graph of g is going to look something like this. It gets a little bit flattened out or a little bit squished or smushed a little bit to look something like that, and you would pick the choice that looks like that. Let's do another example. So here we are told this is the graph of f of x, and it's defined by this expression. What is the graph of g of x? And g of x is this. So pause this video and think about it again. All right, now the key realization is it looks like g of x is, if you were to take all the terms of f of x and multiply it by 2, or at least if you were to multiply the absolute value by 2, and then if you were to multiply this -2 by 2. So it looks like g of x is equal to 2 times f of x. And we could even set up a little table here. This is another way that we can think about it. We can think about x. We can think about f of x. And now we can think about g of x, which should be 2 times that. So we can see that when x is equal to 0, f of x is equal to 1. So g of x should be equal to 2 because it's 2 times f of x. So g of x is going to be equal to, or g of 0, I should say, is going to be equal to 2. What about when at x equals, let's say when x equals 3. When x equals 3, f of x is -2. G of x is going to be 2 times that because it's 2 times f of x. So it's going to be -4. So g of x, or I should say g of 3, is going to be -4. It's going to be right over there. And then maybe let's think about one more point. So f of 5 is equal to 0. G of 5 is going to be 2 times that, which is still going to be equal to 0. So it's going to be right over there. And so the graph is going to look something like this. I'm just connecting the dots, trying to draw some straight lines. it's going to look something like this. You can see it's kind of stretched in the vertical direction. So if you were doing this on Khan Academy, it'd be multiple choice. You'd look for the graph that looks like that. Let's do a few more examples. So here we are told this is the graph of function f, fair enough. Function g is defined as g of x is equal to f of 2x. What is the graph of g? So pause this video and try to figure that out on your own. All right, now let's work through this. And the way I will think about it, I'll set up a little table here, and I'll have an x column, and then I'll have a, well, actually just put g of x column, and of course g of x is equal to f of 2x. So when x is, and actually let me see, when x is equal to, I could pick a point like x equaling 0. So g of 0 is going to be f of 2 times 0. So it's going to be f of 2 times 0, which is still f of 0, which is going to be equal to a little bit over 4. So, which is equal to f of 0. And so they're going to both have the same y-intercept. But interesting things are going to happen the further that we get from the y-axis, or as our x increases in either direction away, or as x gets bigger in either direction from 0. So let's think about what's going to happen at x equals 2. So at x equals 2, g of 2 is going to be equal to f of 2 times 2, 2 times 2, which is equal to f of 4. And we know what f of 4 is. F of 4 is equal to 0. So g of 2 is equal to f of 4, which is equal to 0. So notice the corresponding point is kind of gotten compressed in or squeezed in or squished in the horizontal direction. And so what you see happening, at least on this side of the graph, is everything's happening a little bit faster. Your whatever was happening at a certain x is now happening at half of that x. So this side of the graph is going to look something, I'll try to draw it a little bit better than that. It's going to look something like this, Everything's happening twice as fast. And what happens when you go in the negative direction? Well, think about what g of negative 2 is. G of negative 2 is equal to f of 2 times negative 2, 2 times negative 2, which is equal to f of negative 4, which we see is also equal to 0. So g of negative 2 is 0. And you might be thinking, why did you pick 2 and negative 2? Well, the intuition is that things are going to be squeezed in, and things are happening twice as fast. So whatever was happening at x equals 4 is now going to happen at x equals 2. Whatever is happening at x equals negative 4 is now going to happen at x equals negative 2. And I saw that we were at very clear points at x equals negative 4 and x equals 4 on f, so I just took half of that to pick my x values right over here. And then, so what our graph is going to look like is something like this. It's going to look something like this. It's going to look like it's been squished in from the right and the left. Now let's do another example. So now they've not only given the graph of f, they've given an expression for it. What is the graph of g of x, which is equal to this business? So pause this video and try to figure that out. All right, the key is to figure out the relationship between f of x and g of x. And what we can see, the main difference is instead of an x here in f of x, we have an x over 2. So everywhere there was an x, we've been replaced with an x over 2. So another way of thinking about it is g of x is equal to f of not x, but f of x over 2. Or another way of thinking about it, g of x is equal to f of 1/2 x. And then we can do a similar type of exercise. And they've given us some interesting points. The points 2, the point x equals 2, the point x equals 4, and the point x equals 6. So let's think about this. Last time, when it was g of x is equal to 2x, things were happening twice as fast. Now things are going to happen half as fast. And so what I would do, let me just set up a little table here. The interesting x values for me are the ones that if I take half of them, that I'm going to get one of these points. So actually, let me write this. 1/2 x. And then I can think about what g of x is equal to f of 1/2 x is going to be. So I want my 1/2 x to be, let's see, it could be 2, 4, and 6. 2, 4, and 6. And why did I pick those again? Well, it's very clear what values f takes on at those points. And so if 1/2 x is 2, then x is equal to 4. If 1/2 x is 4, then x is equal to 8. If x is equal to 12, then 1/2 x is 6. And so then we could say, all right, g of 4 is equal to f of 2, which is equal to 0. That's why I picked 2, 4, and 6. It's very easy to evaluate f of 2, f of 4, and f of 6. It gave us those points very clearly. So g of 8 is going to be equal to f of 1/2 of 8, or f of 4, which is equal to -4. And then g of 12 is equal to f of 6, which is half of 12, which is equal to 0 again. So then we can plot these points and we get a general sense of the shape of the graph. So let's see, g of 4 is equal to 0. G of 8 is equal to -4. All right, over there. And then g of 12 is equal to 0 again. So everything has been stretched out. So there you go. It's been stretched out in at least in the horizontal direction is one way to think about it. In the horizontal direction. And you can see that this point in F corresponds to this point in G. It's gotten twice as far from the origin because everything is growing half as fast. You input an X, you take a half of it, and then you input it into F. And then this point right over here corresponds to this point. Instead of happening at 4, this vertex point, it's now happening at 8. And last but not least, this point right over here corresponds to this point. Instead of happening at 6, it's happening at 12. Everything is getting stretched out. Let's do one